Uh, and just again, reminder about the homework assignments that the next one is due on Tuesday. So we still have one more that's extended because of the cancellation we had recently. But then after that, we'll be back on our regular schedule. So what we're going to do today is, in some levels, a continuation of last time. So last time we talked about quantum numbers and orbitals. So we sort of developed the idea that atoms, and specifically multi-electron atoms that we're getting into now, they have many different possible energy levels that are defined by quantum numbers. And we call those, we have, shells that are defined by the first quantum number, subshells, and then individual orbitals that fall within those. And we kind of went through all that and talked about the shapes of the orbitals as well. So what we're going to talk about mostly today is how to decide how do we divide up the electrons into those different subshells and different orbitals. So we have multi-electron atoms now. We want to determine which subshells have how many electrons in them and go from there. So that's what's going to be the topic of today. It's called electron configurations. So first, we're going to just do a couple example problems sort of related to what we talked about last time, just to reorient ourselves on quantum numbers and orbitals. So the first one here, what is the smallest principal quantum number that has d orbitals? So here we're kind of, in some sense, working backwards through the relationships between the different quantum numbers. So we're looking for a principal quantum number. So that's going to be the first one, which we abbreviate as n. And we're telling you to find the smallest value of n in which you would have the possibility of having d orbitals. So if you recall, those letters that define the different types of orbitals, we have s, p, d, and f. They refer directly to the second quantum number, which is abbreviated as L. So here what we're telling you for d orbitals, that's our L value, and that corresponds to L equals 2. S is L equals 0, P is L equals 1, D would be L equals 2. So we're looking for the smallest value of n in which L could be 2. And so what we recall then is that n can have any of these values that are positive integers, 1, 2, 3, 4, and so on. But then the value of L is sort of limited by what value of n you have. So L starts at 0, goes up by integers, but then the maximum value of L you can have is n minus 1. So if L equals 2, again, we have to sort of work backwards to these relationships. If L equals 2, the value of n needs to be larger than or equal to 3. Okay? If n was equal to 1 or 2, you could not possibly have L equals 2. That would be too large of an L value to have in the first or second shell. So only when n equals 3 or anything higher than that would you have the possibility of L being equal to 2. Those are the only times when you would see D subshells. Okay, so that's one example that just sort of goes through relationships between quantum numbers. This is another one here that talks about the number of orbitals that have a quantum number. So you may see problems like this on the homework assignment where we give you a certain set or subset of quantum numbers and asking you how many orbitals are in there. Today we're going to learn what's the maximum number of electrons you can put in there, which is a related sort of relationship. But we have here just how many orbitals have the quantum numbers NL equals 6,6. Now, you want to make sure you read these questions closely because we did learn some relationships last time that are pretty simple, but you don't want to just blindly follow them because there is another possibility that does come up in this problem. So we learned last time that in a shell, which is defined by an n value, the number of orbitals equals n squared. And in a subshell, so if we give you an L value, either by itself or in this case, along with an n value, then the relationship that would possibly be applicable is the number of orbitals is 2L plus 1. So you might be tempted to just say, well, okay, I have L value at 6, 2L plus 1 is 13, done. But what we have to also make sure we evaluate before we start the problem is this an even allowed set of quantum numbers? And just like we saw in the last problem, if n equals 6, the possible values of L can only go up to n minus 1. So L can only be 0, 1, 2, 3, 4, or 5. L equals 6 is not allowed if you have n equals 6. And so what that means is there would be no orbitals that would have these two quantum numbers. That's not an allowed pair of n and L values. So the correct answer for this question would be 0. because you can't have that combination of n and l values in any type of orbital. So if L is going to be 6, n would have to be at least 7, or if n is equal to 6, L cannot be bigger than 5. So when you're approaching problems like this, make sure you also quickly evaluate the relationships between quantum numbers, because if it's an invalid set of quantum numbers like we have here, there would be no orbitals, or there would be no electrons that could have those quantum numbers, because those two just can't go together. All right. And then finally, I think this is the last one here. Which of the following orbital designations is incorrect? And so again, this is kind of similar story, looking at the relationship between these different letters and the L values that correspond to them, and whether all these combinations would even be an allowed set. And so again, key things to remember for this problem are the letters S, P, D, and F, which correspond to L values of 0, 1, 2, and 3. So we want to check to make sure that the letter we're giving matches up with the L value. In all these cases, it does, so that's not going to be the issue. But then what we also have to remember is that the values of L can only go up to n minus 1. So if we look at the first one here, n equals 2, L equals 0, that's an allowed pair because L can be 0, that's the smallest possible value, and that would correspond to 2s. S is L equals 0, so that one's fine. If we go to letter B here, n equals 3, L equals 1, that's an allowed combination. If n equals 3, L can be 0, 1, or 2. 3p would be correct for that. If we go to the letter C, n equals 4, L equals 2, that's also a fine combination. That would correspond to 4d, so nothing wrong there. But again, letter D here is the same concept we just had in the last problem. N equals 3, L equals 3. If that existed, you would call it 3f, but you cannot have n equals 3 and L equals 3 at the same time. The maximum value of L for n equals 3 would only be 2. So this one is the one that would have an incorrect designation, because again, it's a combination of quantum numbers that don't go together. So I'm emphasizing that because that does come up in some of the questions. And if you're just too blindly focused on sort of, this picture here with the letters, or if you're just too blindly focused on the relationships I gave you in the last problem with n squared and 2L plus 1, you might miss a simple thing like this, which is that some combinations of quantum numbers aren't allowed. And then by definition, we couldn't have those being together like we saw here. And then the last one here goes back to what we talked about with the shapes of orbitals. So we only have to worry about S, P, and D orbitals. And when you're doing a problem like this, you should really remember there's key designation between them first and foremost. So S orbitals are always spherical. Those are probably the easiest ones to identify and to visualize. P orbitals would have sort of a figure 8, or what we call dumbbell shape. Sometimes they would have 2 lobes. The ones that have 4-leaf clover shapes like this are all of the d orbitals. There is one d orbital that's a little bit weird and has a sort of donut shape around a dumbbell, but nonetheless, most of the d orbitals look like this. So right away, we can identify this as a d orbital. So that takes out choice A, because the p orbitals would not have 4 lobes, they'd only have 2. But then we have to decide which one it is. Now, the names for the d orbitals do give you some idea about their orientation. So if we look at these lobes here and the way that the coordinates are labeled, the lobes for this orbital orient along the x and the y directions. So it's going to be one of the d orbitals that's in the xy plane. So that gets rid of choice D. But then which of these two is it? We have to remember that those two are very similar to each other. Dx squared minus y squared and dxy. Those are both valid designations for d orbitals, and they both sort of have their orientation in the xy plane. So the one that has the lobes directly along the axis, these are directly along y, directly along x in this direction, that would be dx squared minus y squared. dxy looks exactly identical to this, but it's rotated 45 degrees where the lobes would be in between the axes. So the other 4-leaf clover-shaped d orbitals, dxy, dxe, and dyz, all have that sort of arrangement where their principal lobes are not right along the axis, but 45 degrees rotated in the plane and in between the axes. So those are the two that are probably the hardest to remember and hardest to distinguish. So that's why I gave it to you here. So just make sure that you're clear on being able to identify shapes. Obviously, Canvas would be a terrible, or WebAssign even would be a terrible platform to ask you to draw pictures into. So you don't have to be able to draw the orbitals, but if we give you a picture, you should be able to identify it by its name for, again, just the S, P, and D orbitals, only 9 possibilities. All right, any quick questions on what we covered last time that we reviewed a little bit just now? All right, so what we're going to get into today then is, again, the idea of how we decide how many electrons go into each orbital, into each subshell in a multi-electron atom. And in order to do that, in order to fully understand this, we do need to introduce our fourth quantum number. So we had the three that we've already talked about, N, L, and M sub L. Those define respectively a shell, a subshell, or an individual orbital. But when we put electrons into orbitals, there is a fourth quantum number that's inherent to the electron itself. So this one is called the spin quantum number. And again, this is the only one that is not a property of an orbital. It's a property of the actual electron. So even if the electron was by itself, not in an orbital, if it was just, traveling through space as a free electron, it would have this quantum number associated with it called the spin quantum number. And it's abbreviated as M sub S. And it only has two possible values, plus or minus 1/2. So this is the only one that's non-integer, but it only has two values. And again, because it's a property of the electron, the values that it has have no relationship to the previous quantum numbers. It's just the electron itself can have either M sub S equals plus 1/2 or M sub S equals minus 1/2. The terminology that we usually use for that is if M sub S equals plus 1/2, we call that a spin up electron. If M sub S is minus 1/2, we call that a spin down. And so when we start drawing diagrams later on that show the arrangement of electrons into orbitals and subshells, what you'll often see is that you'll have an upward facing arrow indicating that M sub S is plus 1/2, or a downward facing arrow indicating that M sub S is minus 1/2. And those, again, they're the only two possibilities. So what it really means for us, it's again, it's a property inherent to an electron. And as you may have learned if you've gotten as far as physics 2, which I'm sure most of you haven't at this point, but if you've taken that or learned it in high school possibly, you'll understand that anything that has a charge and that's moving through, that's spinning, is going to have a magnetic field associated with it, the sort of right-hand rule you might have learned. And that's basically what this spin quantum number is. So it's the direction of the electron's magnetic field. An electron is a charged particle, so it has its own inherent magnetic field associated with it, and M sub S refers to the direction of that magnetic field. Again, this physical definition is not terribly important for us, but just to be a little bit familiar with it, I'm including that here. And so then what we have, whenever we have an electron in an atom, where we're going to put it into a specific orbital in that atom, that each electron is going to have a set of four quantum numbers that defines it. It's going to have an NL and M sub L value that tell you which orbital it's in. So these three together, as we've already talked about, define the orbital. But then that electron is also going to have its own associated M sub S value. So it'll have a fourth quantum number M sub S that also is specific to that electron. All right. So the whole point then is that for however many electrons we have in our atom, each one is going to have a set of M sub L, and M sub S values associated with it. All right, so then that leads us to another principle that's important when we're doing this, which is called the Pauli exclusion principle. And again, Pauli here is not too pleased about this, but it's very important for us to understand nonetheless. So the Pauli exclusion principle that he came up with states that if we're putting electrons into an atom, as we just said, they're all going to have their set of four quantum numbers that defines them. No two electrons in an atom can have the same set of quantum numbers. So every electron is going to have a unique set of those four quantum numbers. You can't have two that are identical. All right. So what are the implications of this rule as far as it goes for putting electrons into orbitals? So remember that the M sub S values can only be plus or minus 1/2. And so what this means is that if you're putting electrons into an orbital, the first three quantum numbers are going to tell you what orbital that is. And then the electron can either go in there with a plus 1/2 spin or a minus 1/2 spin, but you can't have two that are the same. And so what that means is you can have at most two electrons per orbital. Because if you're going to put electrons into orbitals, one would have to go in with a positive 1/2 spin at spin up. The other one would have to go in with the opposite spin in order for them to have a different set of quantum numbers. If you tried to put more than two electrons in an orbital, or you try to put two of them in with the same spin, then that would result in those two electrons having the exact same set of quantum numbers, which is not allowed by this principle. So to take it again a step further, which is hopefully obvious at this point, if an orbital does have two electrons in it, which is the most it can have, the spins are what we would call being paired, which is the chemistry way of saying opposite. One of those electrons is m sub s equals plus 1/2. The other has to be m sub s equals minus 1/2. All right, so that's the situation. When we start putting electrons into orbitals, every orbital in the atom, which is going to be defined by the quantum numbers that we've been talking about, is going to have, it's going to be either completely empty, that could be possible. It could have one electron in it, or it could have two electrons in it, but it never has more than that. And if it has two electrons in it, one of them spin up, one of them spin down. So that's the situation that we'll see when we start dividing electrons into orbitals and subshells. Now, with these additional ideas in hand now, we can start talk about relationships that tell us the maximum number of electrons that we can have that are in either a shell or subshell. So there's two electrons maximum per orbital. How does that then translate into the number of electrons that can be in a given shell defined by the principal quantum number n, or in a subshell defined by n and l together? So what we learned recently, and we sort of reviewed it a little bit today, is that in a shell, the number of orbitals is n squared. So because there's a maximum of 2 electrons per orbital, all that means then is that, double arrows, I'm terrible at drawing, the max number of electrons in a shell is equal to 2 times n squared. So each orbital can have up to 2 electrons in it. There's n squared orbitals, so 2n squared will be the maximum number of electrons you can put into a given shell. And again, that's defined by the n value. And then in a subshell, which is defined by a pair of quantum numbers n and l, or anytime you're given the l value, we're going to use this relationship here, even if we don't specify what n is. The number of orbitals in a subshell we saw was 2l plus 1. That's how many unique m sub l values there are that define each orbital. And so what that means then is that the maximum number of electrons is 2 times 2l plus 1. Or if you're someone that likes to distribute terms, I suppose you could write it as 4l plus 2, but they're mathematically equivalent, obviously. Okay, so those are the key relationships now, where we're just taking what we learned last time and extending it one step further, knowing now that there's a maximum of 2 electrons in each orbital. So if we have an example of this, just a quick example, if we're in the third shell, which is n equals 3, the number of electrons that we can put into that shell is just 2n squared, which is 2 times 3 squared, or 18. So in any given atom, if there's 18 or more electrons, at most 18 of those can be in the third shell. That's the maximum number we can put into that third shell. And then for each of the subshells that are in the third shell, so for 3s, the number of electrons that can go into 3s would be, it's 2 times 2l plus 1, so s is l equals 0. So there'd be a maximum of 2 electrons in the 3s subshell. For 3p, where l equals 1, the maximum number of electrons would be 2 times 2l plus 1. Now l is equal to 1. So that's 6. And then for the 3d, the number of electrons, 2 times 2 times 2 plus 1, l equals 2 for a d subshell, which is 10. So if you put 18 electrons into the third shell, the way they would have to be arranged because of these relationships is you would put 2 of them into 3s. There's one 3s orbital, so it would get 2 electrons at most. 6 of those would end up in the 3p orbitals. There's a set of 3 identical orbitals just oriented differently that would get those 6 electrons. And then you have 5 d orbitals that we talked about. So with 2 electrons in each of those, that would be a maximum of 10. So that's how the electrons would then divide up into the different subshells that you would have in this third shell. So 18 total, 2, 6, and 10 would be how they would divide up into the different subshells that you have. So these relationships are also fairly useful for us, although as we will see in a little bit later today, is that a lot of these relationships for the number of electrons that you can put into a subshell, we can read directly off the periodic table. So that makes it helpful for us, so we don't necessarily have to memorize or use these relationships all the time, as long as we have the periodic table available, which you always would for this course. Okay. But before we start getting into more details about how to divide them up into different subshells, what we also have to understand then is the factors that influence the energy of electrons when they're placed into different orbitals and different subshells. Because the whole idea here that we're working towards is that we're going to take all the orbitals that are available to us in the atom, we're going to order them from lowest energy to highest energy, and we're going to put the electrons in that order. So the lowest energy subshells are going to get filled first, and then we just work on up and up and up until we've added all the electrons that we have for that atom. So we have to understand, how do we decide, or how do we determine what order those subshell energies would appear. So there's sort of two main things that underscore the energy of an electron when it's bound to a nucleus. And these are purely electrostatic interactions. So the electron is negatively charged, the proton is positively charged, so they're going to attract to each other. So that is going to influence also the energy of the electron. Then is that attraction between the electron and the protons in the nucleus. So if we have more protons in the nucleus, that's going to result in a stronger attraction, which results in more negative energy. Lower, I should say. So if you're considering the energy of a 1s orbital, all else being equal, the more protons you have in the nucleus, the lower the energy of that orbital is going to be, because the attraction between the electrons and the protons would get stronger. And this one, that was also in the Bohr equation to some extent, but we'll sort of skip that insight for now. The other thing that kind of then plays into this is the distance from the nucleus. So the closer the electron is to the nucleus, the stronger the attraction. And that's, again, a core principle of any sort of electrostatic interaction. If you have a positive and negative charge interacting with each other, the closer they are together, the stronger that attraction will be, which also then would lower the energy. So as we kind of discussed already in sort of broad terms, the different quantum numbers that we have, and especially the n value, the principal quantum number, 1, 2, 3, 4, and so on, is related to, on average, how far away from the nucleus the electron would be. So the closer the electron is to the nucleus, the stronger the attraction would be, the lower the energy of that subshell we would expect it to be. But then there's sort of the opposite sort of term that we have to consider here is electron-electron repulsion. So when you have more than one electron present, those electrons are going to be attracted to the nucleus, but then they're also going to be repelled by one another. So whenever you have electrons that are sort of in the same region of space, those are going to be repulsive forces that are destabilizing, that raise the energy. So as we're moving out towards multi-electron atoms, in hydrogen, you don't have to worry about this because there's only one electron. But in multi-electron atoms, which is everything else on the periodic table, the electrons experience repulsive forces or repulsive interactions because of the other electrons that are present. So these interactions are destabilizing and increase the energy. So there's sort of a balancing act the electron has to play. Electrons want to be at the lowest energy possible that's available to them, but they have to then, balance getting close to the nucleus, which would lower the energy, but also trying to stay far away from all the other electrons because that would raise the energy if they're too close together. And so it's kind of two competing forces that come into play when determining the overall energy of that. So how then that relates to orbitals and their relative energies comes from two concepts called shielding and penetration. And so if we have a situation with multiple electrons, one thing that can also happen is shielding. So again, the electrons, they want to have as strong of an attraction with the nucleus as possible. But if there's multiple electrons, there's going to be some electrons that are closer to the nucleus than they are that's going to block out some of that positive charge. And that's what shielding refers to. So shielding is the idea that sometimes the nuclear charge experienced by an electron is reduced because of electrons that are closer to the nucleus than that one. So if you have inner electrons that are closer to the nucleus, that are in subshells that have smaller radius, if you want to think about it that way, these inner electrons block the outer electrons from feeling the nuclear charge. So we call this the effective nuclear charge, Z effective, ZEFF, and that's going to be smaller than the total nuclear charge for the outer electrons. And so what this leads to is the idea that, in general, the subshells that are further away from the nucleus end up being higher in energy, just like we saw in the Bohr model. The Bohr model was a lot simpler. It just had circular orbits, and it said that the further and further away you get, you're going to have less attraction to the nucleus and higher energy. And the same thing is true for multi-electron atoms with the sort of quantum mechanical wave function model of orbitals, which is that the electrons that are further away, both because they're not as close to the nucleus and because some of the electrons that are closer sort of block them out, they're going to experience less of that positive charge, and that's going to raise their energy. So long story short, the closer you are to the nucleus, the lower your energy. But then another factor that influences how close on average the electron is going to be what's called penetration. So if we're thinking about it, we've said that the value of n, 1, 2, 3, 4, and so on, is going to, on average, sort of tell you how far away the energy level is from the nucleus. So then what happens, though, if you're in the same shell and you have two different types of orbitals or two different subshells, for example, 2s and 2p, which of those would, on average, be close to the nucleus and then lower in energy? Because those both have the same principal quantum number. They're both n equals 2. So how do we decide which one of those is going to be the one that's, on average, closer to the nucleus and then thus have a lower energy? In multi-electron atoms, these two aren't at the same energy anymore, so how do we know which one is lower versus higher? So this comes from a concept called penetration, which is the ability of an orbital or an electron in that orbital, if you think about it in those terms, to get close to the nucleus. And when this happens, it reduces the effect of shielding. So penetration is the effect that kind of partially reduces the effect of the shielding that the inner electrons would have on outer electrons. So if we're comparing 2s to 2p, to understand this concept about comparing these two, we need to look at those radial probability functions again, 4 pi r squared psi squared, which again tells us the relative probability of the electron being a certain distance from the nucleus. And we also introduced the concept of radial nodes before, which was important. So if you have a 2s orbital, we're going to do 2s here in blue. Remember that it has one radial node. N minus L minus 1 is the number of radial nodes. So it had a probability density that looked kind of like this. It had a little peak there, and then a bigger peak further away. So that would be your 2s. Now, if we do 2p in red here, 2p does not have any radial nodes, so it's going to have a simpler probability density function. And actually, the most probable radius for 2p is a little bit closer than 2s. I'm going to try to draw that accurately. They're not that different from each other, but it's a little bit shifted. The peak is a little bit shifted for us. So it looks kind of like this. So the most probable radius is a little bit less for 2p than 2s. I'm going to show 2p is going to be the one here in red. But what happens is because of this little probability region here that's close to the nucleus for 2s, you would say that the 2s orbitals are better penetrators than 2p. They have this little probability of being close to the nucleus, which alleviates some of the problems with shielding. And so even though 2p's most probable radius is a little bit higher than, a little bit lower than 2s, this ability to get close to the nucleus because of this radial node here allows the 2s orbital to be lower in energy. So the net story of this, whether you fully follow this explanation or not, is that the energy of the 2s orbitals are lower than that of 2p because 2s is a better penetrator. All right, and it's again because of the shape of the probability density being different and having this little region here that's close to the nucleus for 2s, which you don't have for 2p. So again, the sort of conceptual description of this is somewhat complicated, but what you then just need to remember and understand is that in any given shell where you'd have the possibility of SP, D, or F subshells, depending on which shell you're in, you may have some or all of those, is always going to be the situation that the S orbitals or S subshell is the lowest energy, and then P, and then D, and then F. So they all follow this pattern. So the first shell where we have all four of these is the fourth shell, n equals 4. So in the n equals 4 shell, the 4s subshell is the lowest in energy, then the 4p, then the 4d, then the 4f, and they always go in that order when you have all those available. So that's going to be the factors that influence the energies of subshells. And there's still a little bit of confusion on this point because even though in a given shell you have this nice simple relationship, S then P then D then F, there is going to be some crossing. So as we'll see in a little bit, for example, 4S is lower in energy than 3D. So there is some kind of overlap of those different subshell energies. So it's we're going to show how you would make those predictions here in a little bit. All right, so another concept we need to understand then for orbitals and subshells is what's called degenerate orbitals. And this doesn't mean that they're in violation of the law. This is a different meaning in chemistry. And so what degenerate orbitals refer to are orbitals that have the same energy. So it turns out, going back to the example we gave earlier as sort of an illustrative point, if you're in the n equals 3 shell, we said that you would have 3 square, which is 9 different orbitals. But it turns out those 9 orbitals are not all at different energy levels. There's some that are the same as each other. And it's pretty easy to make the prediction about which ones those are because orbitals that are in the same subshell that means they have the same N and L values, are degenerate with each other, meaning they have the same energy. So the simplest example of this, the first time that it shows up is in the 2p subshell. For 2p, L equals 1. So we know that there's 2 times L plus 1, which is 3 orbitals. We talked about last time how they all have, they're designated as px, py, and pz. They all have the same shape, but they're pointing in different directions. But this tells us now that all 3 of these have the same energy. So basically what that means is px, py, and pz should be more specific. 2px, 2py, and 2pz, as long as they're in the same subshell, they're all degenerate with each other. Okay? So whenever you have a set of multiple orbitals in the same subshell, which occurs for the p subshells where there's 3 orbitals, or the d subshells where there's 5, or we'll sometimes see the F subshells, which have 7 orbitals in them. In those situations, all the orbitals that are in that same subshell would all have the same energy as one another. That's called degeneracy. All right, and again, that comes into play when we start ranking orbitals and subshells in terms of energy. Knowing that all the orbitals in the same subshell are at the same energy is going to be useful for us as we move forward and makes things at least a little bit less complicated. So then finally tying it all together and getting into what you're going to actually have to be able to do then, this is all sort of background and understanding, but now we're going to talk about what you're actually going to be doing is, again, adding electrons to orbitals, figuring out in a multi-electron atom how many electrons each orbital has, and that follows what's called the Aufbau Principle. Named the German flag here is because, as you might have guessed, Aufbau was German, so that's all that means. But anyway, the Aufbau Principle is what's sometimes called the building up principle. I briefly stated this earlier, but what it means is that electrons are going to be added one at a time to the lowest energy sublevel that's available. That is Germany. Aufbau is a German word, as you might have guessed. If you don't know German, that's okay. We don't test you on that in this class. But I've been there. Actually, I've not been to Germany, as it turns out. I would love to go though. I'm sure it's a beautiful place. But a lot of early chemistry did come from Germany. It's one of the chemistry powerhouses in the world. So you'll see German names and German words a lot as you go through your chemistry sequence, not just in this class, but others. For example, Heisenberg is German, Schrodinger is German. We've seen some German names already that I didn't really specifically mention. I think Aufbau is a word. I don't think Aufbau is a name. I think Aufbau is a word that means building up. Don't quote me on that because I know zero German. All right. But anyway, the Aufbau principle tells us is that electrons are added one at a time to the lowest energy subshell that's available. So in other words, we fill subshells from lowest energy to highest energy. So you're going to start with the lowest energy subshell, you're going to fill it up, and then once that's full, if you have more electrons, you're going to put those into the next highest subshell. You're going to fill that up, and then you're going to keep going up and up and up. So you fill one subshell at a time. Once that subshell is completely full, then we move on to the next one if we still have more electrons that need to go in there. So that then gives us, if we follow this Aufbau principle and Pauli exclusion principle, which we introduced earlier, that says you cannot have more than 2 electrons in the same orbital. If we follow those 2 rules together, that gives us what's called the ground state configuration. We talked about earlier that ground state means the lowest energy state. We talked about it in the context of hydrogen, but every atom has a ground state, which is basically the lowest energy arrangement of electrons that are possible. And that comes from following the Aufbau principle. So the ground state configuration is the arrangement of electrons into the different subshells available, and it's the arrangement that has the lowest possible energy. So what we'll have then is we're going to have a list of subshells, and we're going to designate how many electrons are in each one. So in an electron configuration, in a ground state configuration, each one's going to be written as is NL with a superscript X, where X will tell us the number of electrons in the subshell. N still means the same thing that we've been talking about, the first quantum number. Or the shell number, as it's often said. And then L still means the same thing as well, although as usual, it's going to be written as a letter, not as a number, S, P, D, or F. S, P, D, F is the only ones that we'll have in the ground state of any atom on the periodic table. So it's some combination of those ones. So you'll write the N value that tells you what subshell, the N and L value together tells you what subshell you're in, 1s, 2s, 2p, 3s, 3p, 3d, and so on. And then X, the superscript, tells you how many electrons are in that subshell. And so each subshell, you're going to tell how many electrons are in it, and then that will designate the ground state configuration of that atom. Now, you might think that this is going to be a challenging task because in order to do this, we have to remember the order of the subshell energies, which one's lowest, then next, and then next, and next, and next. And, if we go down the periodic table, we might be filling up probably at, close to 10 or more subshells are going to be filled up. That's a lot to remember. And we have to remember how many electrons can go into each subshell. There's a lot to remember, but the nice thing for us is that the periodic table gives us all of that information. So if you ever were wondering why is the periodic table shaped the way it is, in large part, it's to convey this information about the order that subshells are filled in and how many electrons would then possibly go into each of those subshells. So what you do when you're doing electron configuration, and I mean, in all seriousness, this is the way that I want you to do it. You might have learned in the past, or maybe the book still has it, this little like diagonal thing. I'm trying to remember how to draw it, but where you'd have like 1s. And you like draw all these diagonal lines. I don't remember how to go, so don't I'm not gonna do it. Because I don't need that because I have the periodic table. So I strongly encourage you, instead of memorizing a little diagram with diagonal lines in it and possibly messing it up when you're sweating bullets in your first exam, just learn how to do it with the periodic table, because you'll have the periodic table in front of you, and then there's no need to memorize anything as long as you understand how this works. So the way the periodic table is organized is that each row of the periodic table, each horizontal row, corresponds to a shell number. So the first row of the periodic table was n equals 1, 2, 3, 4, 5, 6, and 7. We'll talk about these ones at the bottom in a little bit, but in the main part of the periodic table, the way this is organized, each row sort of relates in some way to the principal quantum number n. And so then when you're filling an atom with electrons, you're going to go in numerical order through the periodic table, and then you're going to progress the different n values as you go down. And then these vertical columns in the periodic table, they represent different subshells within those principal quantum numbers. And so these first two columns of the periodic table, which I'm going to highlight in blue here, that's going to represent the NS subshells. So as you're moving through hydrogen, you're in n equals 1, and this is S. So hydrogen is going to have a 1s electron. And then when you move down to helium, those electrons are going to go into 2s, and so on. So that's the S subshell. Then the ones over on the far right here. Now, what I also need to show here, though, is that helium's in a weird spot on the periodic table. Helium is also a 1s. The second electron in helium would also go into 1s. It's moved over to that side of the periodic table for reasons we'll get into later. Basically, its chemical properties are more similar to the ones below it, even though it has only s electrons. It's in kind of a weird spot, but that'll be obvious later on. Over here on the very far right, these columns here that I'm going to put red lines through, that's going to be, includes those ones as well. Those are going to be your P subshells over here. So what you'll see is that the P subshell doesn't start until row 2, because the first P subshell we have is 2P. We don't have a 1P subshell, so that's why there's no block up here in row 1. So down here, when we're in this part of the periodic table, that's going to be 2P. And also the number of elements in that block, the number of columns that you have, tells you how many total electrons you can put into it. So you may not remember this, but we determined earlier that you could put a maximum of 6 electrons into a P subshell. And you'll notice that there's 6 columns in this P block here. So that'd be 2P1, 2, 3, 4, 5, 6 when you're filling that up with electrons, okay? And then the middle part here, which is my favorite part of the periodic table, though we won't talk about it a lot in this class. This middle part, which I'm going to do in green here, these are the D subshells. Now, one thing to remember with the D subshells is that it's not actually ND, it's N minus 1D. Sorry, I'm going to do that in green to make it more clear. So that's going to be N minus 1D. So here, where that first one starts, we're in the 4th row of the periodic table, but this is N minus 1. So this would be 3D. 3D is the first D subshell. So even though it's in the 4th row, this row here represents the 3D, and then 4D, and then 5D below that. Okay? So those are the D ones. And then the ones down here, which we won't we won't deal with them as much, but we need to make sure we know where they are, is down here we have these two that are sort of cut out from the main periodic table. And those are going to be the F subshells. These are technically n-2F. And so if you're looking closely where there's sort of a discontinuity in the periodic table, here we see that after atomic number 57, we have a skip to 72. And that's because this block here should be arranged up there. So you could make the periodic table that doesn't cut these out and just puts them all in the same row. But then your periodic table would be like a terrible aspect ratio and hard to put on a single sheet of paper. So we cut them out and put them below. So this row here, the first of these two, should go in between 57 and 72 in the sixth row of the periodic table. This one here goes in the seventh row of the periodic table where there's a gap between 89 and 104. It would go there. This is n-2F. So this one comes from the sixth row, so it's the 4F block. This one comes from the seventh row, so it's the 5F block. Okay. So we're going to go through a lot of examples of this. But to sort of give you a preview of where this is going, the key idea here is that as we're building up electron configurations, we figure out what's the atomic number of the atom. That's the total number of electrons that it would have, stuff that we learned back in chapter 1 or earlier in chapter 2. And then once you know how many electrons it has, you just progress in numerical order through the different blocks of the periodic table until you get to that element. And you fill up all the ones that come before it, and then wherever that element is where you would stop. So it'll make more sense as I go through it, but this is how the periodic table is organized. And the more you practice this, I think the more second nature it will become. So we'll do several examples today, as I said later on. The last thing we need to introduce before we do examples of how to define electron configurations is called Hund's rule. So Hund's rule deals with how we fill degenerate orbitals. So electron configuration, in most cases, it's just going to show you how many electrons each subshell has. And that's typically enough for what we're going to be doing. But in some cases, it's also important to understand how is each individual orbital filled. So if you have an electron configuration that ends with 2p4, you know that you have 4 electrons in the 2p subshell, but sometimes it's also important to think about, well, how many electrons go into one of those p orbitals, how many electrons go into the second and the third, and so on. So it's talking about the configuration of individual orbitals sometimes comes up as well. And to understand how to properly do that, we need to introduce yet another rule called Hund's rule. So the definition here, there's technically more than one Hund's rule, but we only need to worry about it in this context for this course. When degenerate orbitals are filled, what you do is you first put one electron into each orbital. And those first electrons all go in with the same spin. You do that before pairing up 2 electrons into the same orbital. Let me write that a little bit better. And the whole idea here is you want to maximize the number of unpaired electrons. So you want to have the most number of unpaired electrons possible if your subshell is not completely filled. If it's completely filled, then obviously each orbital is going to have 2 electrons in it, one spin up, one spin down. But for partially filled subshells, you want to follow this rule to make sure that you're maximizing the number of unpaired electrons. So 1 electron into each orbital first, all with the same spin, and then you start pairing them up after that if the subshell is more than half filled. And why this happens, not so important for us, but in case you're curious, first of all, the idea of putting 1 electron into each orbital first is to minimize electron-electron repulsion. So as we kind of said earlier, electron-electron repulsions are bad. And so 2 electrons in the same orbital are going to repel each other more strongly than 2 electrons that are in 2 different orbitals. Because the 2 electrons that are in 2 different orbitals are going to be occupying different regions of space on average, not as close together as each other. So that minimizes the number of electron-electron repulsions that you have. Why do they have to have the same spin That's certainly beyond this course, but if you ever take quantum mechanics course like PChem 2 later on in your life, or the survey PChem course probably covers a little bit too. That's what's called exchange correlation. So electrons that all have the same spin as each other, that are same energy level, that is sort of a stabilizing interaction that lowers energy a little bit. But the reasons why are fairly complicated, so we won't get into that. Now, when does this matter? When does Hund's rule even come into play? It only comes into play when you have degenerate orbitals, as we said. So it doesn't matter in the s subshells because the s subshells only have a single orbital. But in the degenerate subshells, which would be the PD or F subshells, if we wanted to find the individual occupancy of each orbital and the relative spins of the electrons in those orbitals, we need to follow Hund's rule to do that. And as I kind of already hinted at, and I'll just write it out here in brief terms, why does Hund's rule even occur? It's because we want to minimize electron-electron repulsions. That's the most important part for us to understand. Basically, by following this Hund's rule, you're spreading out the electrons as much as you can within that subshell, not forcing them to be too close together. Okay. But as we said, the vast majority of what you're going to be doing in this course and all the homework questions that you'll deal with are going to be involving electron configure. Yeah, go ahead. Sorry. So what we have to be able to do from a practical standpoint and for a lot of the homework and test questions, I mean, some of the concepts that we covered today are important. I don't want to downgrade them to triviality, but at the same time, most of the questions are going to be, what's the electron configuration of this element? Or they're going to give you an electron configuration and ask you to identify the element or pick the correct one, stuff like that. So you have to learn how to do that. So let's go ahead and do several examples of this. We're not going to start with the very easiest ones because those are a little bit trivial. Let's start with atomic number 5, which is boron. Okay. So in order to do this, we are going to have to flip back to that periodic table. So we're going to do two things here in these examples. We're going to write out the ground state electron configuration, which, as we said, just specifies how many electrons are in each subshell. And then we're also going to show in these diagrams down here the population of each individual orbital. Okay, so if we go through and do this, let's go back to the periodic table. All right, so boron is right here, number 5 in your periodic table. I should get my pointer up. I'm starting to worry that my pointer is the reason that my tablet crashes sometimes, but I'll take the risk here and use it. If my pen stops working, then I'll know it's the pointer's fault because I just opened it now. Okay, so anyway, atomic number 5 is right there. So we want to figure out the electron configuration for that. Again, what we do is we just go in numerical order until we get to that element, and we just progress through the different parts of the periodic table to get there. So we start at atomic number 1. This is the 1s subshell, so it's going to be 1s1. Remember, helium is a weird one, so it's 1s2. So we go 1s2. Then atomic number 3 is in the second row of the periodic table, also in the s block. So it's going to be 2s1 and then 2s2. So 2s is also filled. And then when we go over to atomic number 5, we're in the 2p block, second row of the periodic table. This is the p block over here on the right. So that's going to be 2p. It's the first element in that block, so it's just going to be 2p1. We stop there because we've added all 5 electrons now. Okay, so it's going to be 1s2, 2s2, 2p1. So that would be the right way to write the electron configuration. There's 5 electrons. We filled 1s, we filled 2s, and that 5th electron goes into 2p, so we write it as 2p1. At the very least, if you're writing out an electron configuration, or if you're doing a multiple choice question that asks you to pick one, make sure it has the right number of electrons in it. So boron is number 5 on the periodic table, so there should be 5 photoelectrons in here. 2 plus 2 plus 1 is 5. So that's always a good first check, although it doesn't mean you're right. It just means you're at least reasonable. Now, the diagrams down here are what we're going to use to show the individual populations of orbitals. So 1s2, in the 1s subshell, there's only one orbital, and so it has to be doubly filled. In order to do that, one electron has to be spin up, one electron has to be spin down. Whenever 2 electrons are in the same orbital, because of Pauli exclusion principle, that has to be true. 2s2, there's only a single orbital in the 2s block as well, so any of the s subshells are going to just have one orbital, so that one's also doubly filled. And then what we have here is 2p1. Now, one thing we need to understand is that if we have 2p1, which of these 3 p orbitals do we fill? The reality is it doesn't matter. Usually to keep things organized, we'll just put it in the leftmost orbital and we'll start with spin up before we do spin down. That's sort of conventional and common just to keep things organized. But what we should understand is that this electron can go anywhere into these p orbitals, and it can have either spin up or spin down, because these three orbitals are all at the same energy. So it doesn't matter which one the electron goes into, it's going to have the same energy. And also, if you only have one electron, the spin, whether it's up or down, is the same energy as well. So there's no energetic preference for that. So we can write it like this. We can write it like that. We can write it like that. Any of the three orbitals will spin up, or we can write it any three will spin down. So all six of those possibilities are valid. That p electron, that last electron there, can go into any of the three p orbitals, either spin up or spin down. There's no energetic difference between any of those possibilities. Again, to keep things organized, I will typically do it left to right, spin up first. Just that's how but that doesn't have to be the way you do it. As long as it's, in this case, any of those six possibilities are all equivalent. All right. So now let's go to one atom over carbon, which is Z equals 6, the sixth element on the periodic table. So I'll open up the periodic table as a separate file. It makes it a little bit faster for me to switch back and forth. Except that's a big file. I hope it doesn't cause any problems. All right. So we're going to go to carbon now, which is number 6 here on the periodic table. And so it's just 1 over from boron, so not much different. But so again, we start numerically. So we go, this is 1s, so 1s1, 1s2. Down to the second row, that's 2s1, 2s2. Now we're back on the 2p, so carbon is the second element there, so it's going to be 2p1, 2p2. So the last thing we would write is 2p2. There's now 2 electrons in the p orbitals. It's just one different than boron, the previous one we did. All right, so for carbon, what we're going to have is the same starting point, 1s2, 2s2. But now we have 2 electrons in 2p, so we've written as 2p2. So it looks trivially different, but when we go down here and do the full configuration with the orbitals, we have to keep Hund's rule in mind. Okay, so that's going to be 1s and 2s. For 2p, though, if we put the first electron in like that, remember that Hund's rule tells us that the second electron has to go into a different orbital with the same spin. So the second electron can go either here, that would be fine, or it could go there, that's fine, or it could be in this one and this one. But the key point is they have to be in 2 different orbitals and they have to have the same spin. Or you could draw them spin down if you wanted to, but again, as long as they follow that rule that they're in 2 different orbitals with the same spin. So both spin down would be fine, there and there, there and there, there and there. So again, there's about 6 different possibilities that are all equivalent, but the key thing is they have to be in 2 different orbitals with the same spin to follow Hund's rule. Okay? I will, again, by convention, write them in this way to keep things organized. But if you're doing a multiple choice question that gives you those different possibilities, you have to recognize that they are all equivalent to each other energetically. So it doesn't matter which 2 orbitals are filled, as long as it's 2 different orbitals. And it doesn't matter whether it's spin up or spin down, as long as they're the same as each other. Okay? But again, this arrangement here we need to do to follow Hund's rule. All right, with more than one electron in the same degenerate subshell, we have to make sure that they have the same spin and 2 different ones. Okay. Any questions on those simpler examples? All right. So what we're going to move on to now are some that are a little bit farther down and introduce a nice little shortcut method for this. Okay, so what we're going to work on now is Na, which is sodium, Z equals 11. And so that's going to move down now to the 3rd row of the periodic table. And we have to understand electron configuration for that. So if we do the full thing, what we would find is we would go start at number 1. So 1s1, 1s2, 2s1, 2s2. We would go all the way through the 2p block, 2p1, 2, 3, 4, 5, 6. That takes us to atomic number 10. So then to get to 11, which is sodium, we drop down to the 3rd row of the periodic table. This would be 3s1. Okay, so we stop at 3s1 for this one. So the full configuration for Na, which is sodium, would be written as 1s2, 2s2, 2p6, 3s1. But what is often done, especially for elements that are further down the periodic table, is that you abbreviate what are called the core electrons with a symbol here. So these electrons here correspond to what's called a noble gas neon. So this is jumping a little bit, but basically this last column of the periodic table here is called the noble gases. So what you often do for heavier elements is you abbreviate all of the electrons that go up to the noble gas with just the symbol for the noble gas. So for sodium here, which is number 11, the noble gas that comes before it is neon, Ne, and we would just write neon in brackets to abbreviate those 10 electrons that are in what are called the core of the electron configuration, and only explicitly show the ones that come after that. So that's sort of an abbreviated shorthand method that's convenient and commonly done. So the way this would work for this example here is that these 10 electrons here all belong to the neon configuration. That's the noble gas that comes closest before sodium. And then the 3s1 would be the last one. So what we could do is we could write this as just neon in brackets with 3s1. So again, to reiterate, what we're doing here is we're taking the nearest noble gas, the one that comes before the element that we're determining electron configuration for, and we put those inner electrons from the noble gas, and we indicate those with brackets. Now, you will need to likely be familiar with both, being able to do the full configuration that lists out all of the subshells, or being able to understand how this abbreviated convention works. So it's not that we're going to replace one with the other, but this is a convenient way of doing it because, as we'll learn later on, not so much in today's class, when you're talking about the properties and the chemistry of an element, it's these outer electrons that matter the most. The ones that come in this inner core here that would belong to the noble gas configuration before it, those don't really matter too much for us. So we often just abbreviate them and only focus on the ones that come after that and write those out explicitly. So if we go to just one element over for magnesium, it's right next to sodium, so it's not much different. But if we were going to just start with the shorthand notation without even writing everything out, the noble gas that comes before magnesium is still neon. So we could just write Ne in brackets to indicate those 10 electrons. And then after that, we jump down again to the third row of the periodic table in the S block. So it's going to be 3s1, 3s2 takes us to magnesium. So we would stop there. It would have now a 3s2 configuration after the noble gas core. So for magnesium, it's very similar, but if we don't want to write the whole thing out, we should just indicate the first 10 electrons belong to the neon configuration with the last noble gas before it. And now it's 3s2. There's 2 electrons in the 3s subshell, or that one 3s orbital. All right. So what this allows us to more clearly illustrate are what are called valence orbitals or valence electrons. These are ones that are the outer electrons that come after the noble gas configuration. We're going to mainly concern ourselves with this concept for main group elements, which are those that are in the S and P block. So the first 2 columns or the last 6 columns, those are the ones that are the most straightforward in a lot of ways, but especially for this concept here. So for the main group elements, these valence electrons are the electrons with the highest principal quantum number. So it would be whatever the outermost S and or P electrons would be. So sodium would have 1 valence electron. It's the electron that's listed after the noble gas core. Magnesium would have 2 valence electrons. Both of these would be classified as valence. So for those main group metals, which are in the first 2 columns or the last 6, whatever outer S electrons you have, and if you have outer P electrons, those would all count as valence electrons. So for the P block elements, the valence electrons would be the S and the P that come after the noble gas. Okay? So we'll talk more about valence electrons later, but I just want to introduce it here since it now makes it a little bit more clear what we're talking about. All right, we're going to do a couple examples now with the transition metals, or maybe just, yeah, well, just one really, and talk about some of the differences here. You can still follow the exact same approach, and you still should, which is using the periodic table to get you from the beginning point all the way to where the element is and moving through the different subshells. But what we have to remember, and the periodic table does tell us this, but it is a point you have to still keep in mind, the S subshell gets filled before the D in these cases. So the NS, which would be either 4S, 5S, or 6S, that's going to end up being filled before the N-1D. So in the fourth row of the periodic table, we would fill 4S and then 3D. The row below that, we would fill 5S and then 4D, or 6S and then 5D. So we have to make sure that we remember that when we're doing these configurations. That's a little bit different than we see for the main group metals, where the last electrons that we put in all have the same N value. And then when we're counting valence electrons for the transition metals, all of those outermost S electrons and all of the outermost D electrons are going to be counted as valence electrons. All right. So if we go through an example, this is a particularly tough one, so I'm just going to give it to you to see what really probably about the hardest we could do in this class. If you handle this one, then you're probably good to go for anything else. Let's do osmium OS. So osmium is pretty far down in the periodic table, but let's see what its electron configuration will look like. We can still follow the same approach. So OS is here, number 76, pretty heavy. And what we're going to do is, again, we're going to look for the noble gas that comes before it, especially for the elements that are way down here. That's going to be a very helpful approach instead of writing out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 5d10, 4p6, and so on. Like, that's a lot to write out. Let's just go to the noble gas before it, which is xenon Xe. So we're going to put xenon in brackets Xe. That's going to be our core. But then after that, we still have a lot to take care of because that's number 54. We have to get all the way to number 76. We have to add those last 22 electrons to that configuration. So after number 54, we come down here to this row, which is the sixth row of the periodic table, and this is still the S block at the beginning. So it's going to be 6s1, 6s2. Things get a little bit confusing in this part of the periodic table because we have the D and the F subshells kind of like intertwined with each other. So if we're just following it sort of by the book, what we would do is after number 56, which is 6s2, we'd go over here. This is part of now the N-1D. This is the 5D block starting here. So it would be 5D1 for number 57, but then it jumps down here to the 4F. So it would go 5D1, 4F, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The full 4F is filled, so it's 14 4F electrons. But then we have to come back up here. That's number 71. We have to go all the way to 76. So then we go to, this is back to 5D, 2, 3, 4, 5, 6. Now that can be a little bit confusing, but if you just remember that when you're in this row of the periodic table, anything after atomic number 57, all of these F orbitals are going to be filled. So what you would have is 6s2, all the 4F are filled, 4f14, and then back up here you'd have 5d, 1, 2, 3, 4, 5, 6. So however you sort of think about it, coming to number 76 here is the sixth column of the D block, so it's going to be 6d electrons. So it's, again, a little bit more difficult to deal with that, but if we write it out, we would get xenon is the core. We saw that we came to 6s2 next, and then 4f14 was completely filled, and there were 6 electrons in, that's 5d, sorry. And so that's a total of 22 electrons plus xenon, so the right number, which is 76. And then how many of these are valence electrons? It's the outermost S and D electrons. So those 2 and those 6 are valence electrons. So this would have a total of 8 valence electrons. We don't count the F electrons as valence, even though they come after the noble gas configuration. So that's why transition metals are a little bit more challenging, because there can sometimes be these F electrons that are intertwined, and only the S and the Ds are going to be the ones that count as valence electrons. The F electrons will never count as valence for these transition metals. As far as I know, we don't, and I don't think we're going to hold you to it any configuration that involves partially filled f orbitals, you're not going to deal with. Those are even more complicated. So if you go down to like the middle parts of those bottom rows, the reality is those are hard to predict because the 4f and 5d or the 5f and 6d orbitals are all like really close to each other. So which ones get filled first and second is not as easy to predict in that part of the periodic table. So we'll leave that be. But for transition metals, this is how you would predict it. So if we're writing out then the orbitals, you'd have 6s2, 4f is completely filled. So you go 1, 2, 3, 4, 5, 6, 7, but then we have 14, so we have to come back and double them all up. So they're all completely filled. And then for 5D, we have 6 electrons, and we need to follow Hund's rule to do that. And again, there's a lot of different ways you can write this, but to keep things organized, what we'll do is 1 electron at a time, 1, 2, 3, 4, 5, all with the same spin, but we still have 1 more electron to put in there, so now we have to double up one of these. Again, to keep it organized, I'll put it in the first one, but it can be in any of those. But you want to maximize the number of unpaired electrons. So you're going to put the first 5 into individual orbitals with the same electron, then we only double up the very last one to follow Hund's rule. Okay, so there would be what we would say that this has 4 unpaired electrons. Those 4 electrons there are all spin up, but they don't have a spin down electron with them. So 4 unpaired electrons. So if you ask questions about number of unpaired electrons, that's how many electrons are spin up that don't have a spin down partner with them. So these 4 here are all individually occupied with all spin up. Now, the other thing that the transition metals bring into play here, we're almost done here. Okay. So the other thing that the transition metals bring into play are a couple of exceptions that you do need to be aware of. There are many more exceptions than this on the periodic table, but we're only going to hold you responsible for these 2. And what we mean by exceptions are situations where you'll follow the rules that I've given you today to predict the electron configuration, but it's not quite right. And that comes because some of the subshells that we're filling, in these 2 examples, it's the 4s and the 3d, those valence electrons, are very close in energy. So whether you completely fill the 4s or whether you start filling the 3d first is hard to predict sometimes. These are the only 2 where we're going to ask you to be aware of those exceptions. So if we go to chromium, which is Cr, which is right here in the periodic table, what we would predict for chromium is that so argon's noble gas before it, so that'll be written as the core, Ar in parentheses or brackets. And then we come down here, this is the 4s part of the periodic table, so 4s1, 4s2, and then to get to chromium will be 3d, 1, 2, 3, 4. Okay, so we would predict that the electron configuration of Cr, chromium, is argon core plus 4s2, 3d4. It turns out, though, that that is not quite correct. In the actual configuration is argon 4s1, 3d5. We take one of the electrons from the s orbitals and bump it up to the 3d. And the reason for this is basically, well, I'll say it in a simpler way, just to make it similar to what we saw before. We're minimizing electron-electron repulsion. It's more than just that. It's more complicated than that. But basically, we're taking, instead of having 2 electrons in the same orbital, we're going to take one of those out and move it up to the d orbitals and allow them to spread out a little bit more. Okay, but you do need to remember, however you choose to rationalize it in your head is not important, but that in chromium, the predicted configuration is not quite right. And then a very similar thing happens with copper, Cu. So the predicted configuration for copper, it's in the same row of the periodic table, but just further down. So it would still be argon noble gas core. Copper's right here, number 29. Argon noble gas, 4s2, and then we'd have 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So copper's the 9th element in that block. So we would predict that it ends with a 3d9 valence configuration. That's what the periodic table would predict for us. But just like chromium, that one's not quite right. And we do really the same thing. We take an electron from our 4s orbital and bump it up into 3d. So it becomes 4s1, 3d10. We're not changing the number of electrons. It's still copper. It's still 29 electrons. It can't have more or less electrons than that and still be copper. But we're just changing the arrangement of them. Instead of 4s2, 3d9, it's 4s1, 3d10. And again, we now have a filled d subshell. So the last thing I'm going to cover today is just how the periodic table is organized. So one of the key points moving forward is that the location of an element on the periodic table, which then specifies how many valence electrons it has and what subshells they're in, is very much related to the properties and the reactivity of that element, how it reacts with other things. So that allows us to then classify elements based on their location in the periodic table. So what we would have here are, I'm going to do a few different classifications for us. But basically, in the periodic table, what you would have is this sort of imaginary dividing line here in the P block. All right, so you have this sort of staircase that starts between boron and aluminum, and you just draw a staircase going down. And essentially, everything to the left of that is a metal, and everything to the right is a nonmetal. So this dividing line in the periodic table, and it in sort of the grossest form, divides metals from nonmetals. Now, within each of those broader categories, though, there's a few different subcategories we should be familiar with. So these first row of the periodic table, I'll do this in color. Don't do that. Let's do it in green here. So this row and this row, along with the metals that come in the P block, so aluminum and down are metals, tin and lead, bismuth and polonium. Those ones there that are either in the S block or the P block, but are to the left of the staircase, so they're all metals, those are called main group metals. So in green, I'm going to be drawing main group metals. So those are all metals, but they occur to the left of the staircase, and they're in either the S or the P block. As we've kind of already mentioned already, these ones here that are in the middle, which are also part of the metals, those are called transition metals. So I'm going to do those in orange in this diagram here. So anything that's in the 3D block of the periodic table is called a transition metal. And then as they're labeled down here, we have lanthanide and actinide series, so we don't need to worry about those too much. And then finally, everything, as we said on the right, is a non-metal. So all these are going to be non-metal groups that are over here. But we have a few that are sort of in between that I want to point out as well. So we have, we're running out of colors here. This color should work. So what we have is these ones here: boron, silicon, germanium, antimony, and tellurium, and arsenic. So those 6 elements that are right along the staircase, we should be familiar with those as being called metalloids. So they're in between metals and nonmetals. They're right on the borderline. So we call those metalloids in purple. And then finally, the last thing I want to point out is that some of these columns of the periodic table have specific names associated with them that we should be familiar with. So this first column here, which is one of our main group metal columns, this is called alkali metals. Everything except for hydrogen. So we should be familiar that hydrogen is actually a non-metal, even though it's in the metal part of the periodic table. I should be clear about that. Hydrogen is a non-metal, but the rest of that column are called alkali metals. And then this column here is called alkaline earth metals. I'm gonna have to, yeah, we're almost out of time. Sorry about that. So just about finished up. So those are 2 of the main group metals that are labeled. And then over here on the far right, we also label these 2 columns. These are all non-metals on the right, but this one are called noble gases. We already introduced that term today. That's that last column of the periodic table. And then this second to last column here are called halogens. So those are the ones we expect to know. The key points are that metals are on the left, non-metals are on the right. The ones in between are called metalloids, and some of them have more specific classifications. So make sure you're familiar with that as we go forward, and I'll see you guys next week.